Let's recap, because this is an important result. We write the law of periods and take the cube root. Cube root of 27 is 3, 3 squared is 9, so our satellite is 9 times closer than the Moon, at 42,000 kilometres. At this radius, a satellite orbits in about 1 day, so it stays in the same place above the equator. This, the geosynchronous orbit, is where we put most of our communication satellites. It's a busy orbit. Another busy region is the low orbit, just above the atmosphere. Here, a similar calculation gives a period of about 90 minutes. For the International Space Station, about 400 kilometres above the Earth, the period is 92 minutes. The astronauts don't get bored with the scenery. Now this brings us to an awkward problem in language. We say that these astronauts are weightless as they drift around inside the space station. But what does weightless mean? In fact, their weight, their gravitational attraction to the Earth, goes as 1 on r squared, so it's only reduced by 12%. They are in free fall. They are accelerating towards the Earth at 88% of 9.8 metres per second. However, the space station is also accelerating towards the Earth at the same rate, and that's why they float around inside it. Well, we're stuck with the word weightless for the experience of free fall. If you were in a falling elevator, you would also feel weightless, even though it is your weight that's accelerating you downwards towards a nasty collision with the ground. So we're left with this awkward, paradoxical statement. Weightlessness is the name for what you feel when the only force acting on you is your weight. Back to orbits. So far, we've discussed them in terms of forces. Let's now discuss them in terms of energy. Again, a small mass m in circular orbit, radius r, about a large mass, capital M. For that circular orbit, radius r, the centripetal force is gravity, g(mm) on r squared. This time, let's write centripetal acceleration as v squared on r. Now we can easily turn this term into kinetic energy. Just multiply both sides by r on 2. This gives half gmm on r equals half mv squared. Now we remember that the potential energy of m and m at separation r is minus gmm on r. So the left-hand side of the previous equation is just minus a half times the potential energy. So minus a half times the potential energy equals the kinetic energy. And since the potential energy is never positive, the kinetic energy is never negative. Save negative kinetic energies and imaginary speeds for when we get to quantum mechanics. So the total mechanical energy, U plus K, is, let's substitute, E equals minus gmm on 2r, or 1/2 the potential energy. So this means that a close orbit has low total energy. You have to do work to get from low orbit to high. Alternatively, if you fall from high orbit to low, your potential energy goes more negative, but your kinetic energy more positive. Here's a toy we can use as a model. In this gadget, the height measured from the top goes roughly as minus 1 on r. So here, close to the Earth, we have U equals mgh proportional to minus 1 on r. So here we have orbits in a minus 1 on r potential. Small r gives very negative potential energy, but high kinetic energy. Large r gives less negative U and smaller k. Somewhat complicated here by friction and rolling, neither of which occur in space. We can also think about the orbits of comets. Fast when close to the Sun, but slow when far away. So keep that in mind. A low orbit, small r, has very negative u and e, but large k. Low orbits are fast. A high orbit, large r, has less negative u, less negative e, but smaller k. High orbits are slow. Here's some simple physics that will probably surprise you. Imagine you're in orbit following another spacecraft and you want to dock with it. How do you catch up? Think about it.